Hello students, welcome back. Welcome back to the world of RoboMate. Students, how are you? Fine? Alright. So we have been discussing the chapter circular motion. Now, let us start with the next module of the chapter circular motion. In this module, we are going to derive a relation between linear velocity and angular velocity. Now students, it's a very, very important module. Alright, so please pay complete attention. Are you ready? Can I start with the module? Alright. Students, what we are going to do in this module? Yes, we are going to derive a relation between linear velocity and angular velocity. For this, I am going to consider a very small particle. This particle is performing a uniform circular motion. What is it doing? It is performing a uniform circular motion. Alright, now let point O be the center of the circular path traced by this particle. Now let us say this particle is at position A. So immediately I can draw a radius vector R from the center to the position of the particle. Yes or no? I can draw a radius vector. Now students, let us say this particle is moving from A to B in a very, very small interval of time delta t. In a very small interval of time it is moving from A to B. Now this arc length AB is also very small, so it is denoted as delta S. Now students, we all know this. As the particle moves from A to B, the radius vector, alright, will move through some angle. Yes or no? So here, let delta theta be the angle through which the radius vector moves in a very, very small interval of time delta t. Is that clear? Here the time interval is very small, arc length AB is also very small, and the angular displacement delta theta, that is also a very, very small angular displacement. Is that clear to you? Any questions till now? No. Now students, what we are going to do here is, we know one relation. Which relation? We know that S is equal to R theta. So using this relation, we can say delta S is nothing but R into delta theta. Now students, can I divide this expression by delta t? Yes, if I divide both the sides by delta t, what I will get? Delta S upon delta t is equal to R into delta theta upon delta t. Now students, what is delta t? Yes, delta t is a very, very small interval of time. Alright, so delta t, we can say it is tending to 0. So since delta t is very, very small interval of time, it is tending towards 0. We can write this relation as limit delta t tends to 0, delta S upon delta t is equal to R into limit delta t again is tending to 0, delta theta upon delta t. Is this clear? Delta t is a very, very small time and it is tending towards 0. Now students, what can we do? We have all studied. Now limit delta t tends to 0, delta S upon delta t is nothing but ds by dt. You have studied this in your 11th standard projectile motion chapter. Yes or no? It is written as ds by dt. So we can write, instead of this particular expression, we can write ds by dt is equal to R. Now again, limit delta t tends to 0, delta theta upon delta t is d theta by dt. So then this will become ds by dt is equal to R into d theta by dt. Is this clear till now? Alright. Now students, we can take this forward and we all know what is ds by dt. Yes, what is ds by dt? Very good. ds by dt is nothing but it is v, which is your linear speed. And what is d theta by dt? Yes students, d theta by dt is nothing but it is omega, which is your angular speed. So then what will happen to that expression? This expression will change as ds by dt is v is equal to R into d theta by dt is omega, so v is R omega. This is the relation. Relation between what? Yes, relation between the linear velocity and the angular velocity. V is equal to R omega. Isn't this very simple? Okay. So students, let us carry this forward and see, velocity, linear velocity is a vector quantity, radius vector, and angular velocity is also a vector quantity. So in vector form, this relation can be written as V vector is nothing but omega vector cross R vector. It's a cross product. Omega cross R. Alright. Now what will be direction of V? Again, it is a cross product. So for cross product we know we can find the direction of the resultant using, yes, in 11th standard you have studied, using your right hand rule. Now let me bring back the diagram. This particle was performing UCM and it was rotating in the anti-clockwise direction. Alright, now if you see here, what is the direction of radius vector? Radius vector is from the center towards the circumference. And what is the direction of omega? Again, right hand rule, particle is moving in the anti-clockwise direction. So according to right hand rule, omega will be acting up. Alright, it is perpendicular to R. Now again, what will be the direction of V? V is omega cross R. Again, you use right hand rule. Omega cross R. So V will be tangential to the circular path traced by the particle. Now see here, this cloud is very important. You see the direction of V? V is tangential. V, R and omega, all the three vectors, they are perpendicular to each other. Is that clear? So this is very, very important, students. So I hope so this module was not that difficult. Remember this relation, V is R omega. We'll be using this in many numericals. Alright. And this particular module can be asked as a question in your test. Alright. Derive a relation between linear velocity and angular velocity. So please be prepared for that. Is that clear? Isn't it very simple? Yes, students, it is simple and you can do it. Alright. So I'll catch you up in the next module. Time for me to leave. Take care. Keep working. Rise and shine.